Okay, let's do a bearing capacity design problem for shallow foundations. Let's say we have 2 meters of clay with a phi of 30 degrees and SU 60 kPa, and we have 5 meters of a low plasticity clay with phi equals 35 degrees and SU equals 100 kPa. And let's say this is over rock, okay? And we have to design a foundation to support, let's say, 450 kilonewtons with a factor of safety of 3, and the foundation is square. Okay, so clearly it doesn't matter where the water table is because we're going to put it up here for design, right? By the way, let's assume that this foundation is not embedded. So the problem begins by realizing that we have this this soil, right, and the water table is here for design, and therefore we know that when we construct in the short term and a little bit after construction, we're going to have undrained conditions because there will be excess pore pressures in here due to the fact that we're going to have a foundation here, right? Or basically load in the soil. So we begin with the undrained analysis. Now here I've selected the undrained analysis to start with, simply because that's the first one that came to my mind. You realize that in the long term the condition will be drained, meaning that excess pore pressures will be 0, and therefore you're going to have to use the phis to determine the drained or to perform the drain analysis. So it doesn't matter, you can start with undrained or you can start with drained. So let's begin with undrained. So we set the factor of safety equal to 3, and that's equal to Q ultimate over Q, right? Which is equal to NC star SU over load times the weight of the foundation divided by the area, right? So if we keep going, here we have 6.14 times SU, and here's where the first question arises. What SU do we use? Well, it should be the SU that is a weighted average over the influence zone. But we don't have an influence zone because we don't have B. So we're trying to get B. That's the whole point, right? I mean, let's just write it here. That's the whole design. So in this case, we have to assume a B or guess a B and see if that works, like we did in class. So the first selection would be perhaps 2 meters by 2 meters, because that way the only zone or the only soil that is influenced, in quotes, would be this one, right? So if this is 2, then you have 2 meters of influence zone below the foundation base, and therefore you are only concerned in your analysis at that point with the undrained strength of that soil. It's more like it. Still, I should make it a little smaller, but anyway, you have to get the idea. So this is 60, right? Because the influence zone again is 2 meters because we adopted a B equal to 2 meter guess. That divided by 450 plus 2 squared times a third of 2. That's the thickness, right? So that's the whole volume. Unit weight of concrete, because we assume it's made of concrete, over 2 squared. That's the undrained factor safety for a 2-meter foundation. Well, this is generic here. 2 meters. The 2-meter foundation is the one we started. Oh, sorry. The 2-meter foundation is the one that we started with at this point in the analysis. So again, 6.14 is the NC star for a square foundation. 60 is the 60 kPa for this layer, which is comprises the whole influence zone. 450 is the load, and then 2 squared times a third of 2, that's the thickness right here, this is the base area, times the unit weight of concrete, all that divided by the area of the foundation, B squared, gives you Q. So Q ultimate over Q. So let's see what this is. Okay, so the answer for the factor safety here is 2.8. Okay, now this is close to 3, so we are okay with this. Therefore, our foundation size, at least for the undrained case, the one that works, is a 2 meter by 2 meter foundation. Okay? Now let's see what happens in the drain case. At this point, you're checking to see if the B equal to B 2 meter foundation works for the drain case as well. Okay, so that's why you choose, of course, B equal 2 meters. In this case, the factor of safety is equal to, so notice here, 2.8, basically the same as 3. Okay, so drained. Factor of safety is 1/2 B gamma prime n gamma star divided by B plus the weight of the foundation divided by area. So I already calculated the Q of here, sorry, right here, right? The Q doesn't change for the same size of foundation. So for 2 meters, this is Q, which is 131.2 kPa. Okay, and this is 1/2 times 2 times 10. Why 10? Because gamma prime is the gamma of the soil, all of which has a unit weight of 20, minus the unit weight of water, which is 10. So 20 minus 10 is 10. And then n gamma star corresponds to the phi of the soil within the influence zone. In this case, our 2 meter by 2 meter foundation has an influence zone that extends only in the CH layer, high plasticity clay. So the only phi we have to use is this one. So what is the n gamma star? The question then becomes, what is the n gamma star for phi equal 30 degrees? Here in your reader, for phi equal 30 degrees, n gamma star is 13.44. Okay, 30 is 13.44 right there. So and the answer to that is, it's actually clear, right? 10 times 13.4 is 134. So here you see that the factor safety, this factor safety is essentially 134 or 131 is 1.07, something like that. So very low, definitely less than 3. So what happens here is that you have a foundation that is going to work in the undrained case, meaning in the short term, but in the long term, when excess water pressures dissipate, it will not work and therefore if you construct it, it will fail. Meaning it will fail after excess pore pressures are dissipated. So what this tells us is that the B equal 2 meter foundation doesn't work. So let's proceed with another guess for B. Let's say B is equal to 4 meters. Just as a guess. Okay? Now the reason I'm guessing that is because the 1.07, that's really low. So I think that if we go much higher, like 4, probably is an overestimation, but it might work. So again, undrained. Factor of safety, 6.14 times SU over 450 plus 4 squared times 4 over 3, a third of 4, right? Times 28. All that divided by 4 squared. It's going to be very large. Let me do something right here. Hold on. Okay. Now, what happens with this value here? Remember that our foundation is resting like this on top of a 2 meter layer, and down here there's a thicker layer of 5 meters, right? So if our foundation is 4 meters in width, the influence zone is 2 meters into the CL and 2 meters into the CH, right? This is the influence zone. So the SU for this soil is 100, and for this one is 60 kPa. So in here we have to insert a weighted average of this 2 over this influence zone. The weighted average is 2 meters of 60 kPa soil plus 2 meters of 100 kPa soil divided by 4 meters total, right? In this case, it's just simply the average as you would take it for two numbers. 160 divided by 2 is 80, right? So what we have here is, let's see, $7.5. So clearly that works because it's larger than 3. Now let's check the drain case for a 4 meter foundation. Factor of safety is equal to 1/2 times 4 times 10. That's gamma soil minus gamma water times n gamma star. Now n gamma star also involves weighted average. So you have the fees here are 30 and 35. Okay? So in here you have an n gamma star that corresponds to the weighted average. Clearly there's 2 meters of this soil and 2 meters of this soil. Therefore the average is just the average between these two numbers, right? So 32.5. 32.5. The n gamma star for 32.5 is somewhere between 18 and 21, right? So let's say 19, 19.5. Okay? And then down here you have the value of Q for 4 meter foundation, 65. Right? So here you have 20 times 20, essentially 400 divided by 65. $6.15. So in the undrained case, the factor of safety is 7. For the drain case, the factor of safety is 6.15 for the B equal to 4 meter foundation. Now, does that work? Yes. But the lowest factor of safety is a little bit too high. That's almost double what we want, or it is more than double what we want, which is 3. So it is likely, I'm not going to continue, you can do it, just want to give you examples here. It is likely that the result will be somewhere closer to 3 meters. What result? Well, the actual, the optimal design, where your undrained factor of safety will be less than 7.5, maybe like 5, and then this one will be closer to 3, hopefully equal exactly to 3. Okay. Now, clearly, if you keep going and changing this number, you will get to the point where the controlling factor of safety, which in this problem is this one because it's always the lowest one, will be equal to 3. Right? So you can change this number and keep going and keep going and keep going until this value is equal to 3. But that is not completely necessary as long as you get close to 3. So from 2.8 to 3.2. So that's close enough, at least for our class. Generally for practice, the same. Okay?